Could you calculate the solubility of mercury 2 sulfide? This is taking a half a step back. We did this last time. Talk to me about how to solve it. You're on the right track, James.
Trying to find my table.
He's looking for that table. Okay, yes. Salomon, since I'm asking you for solubility, I'm asking you for grams per liter, correct? We are going to need the molar mass. In order to get the molar mass, we're going to need the formula. What's the formula of mercury 2 sulfide?
Is that KW? No, that's one.
The formula of the compound. HGS. We got to know that because mercury 2 sulfide is it Hg2S or HGS2 or, well, it's just Hg2S. So now we can figure out the molar mass of it. Molar mass, I got 232.656 grams per mole. Are you checking my math? Mercury is 200.59 and sulfide is 32.066. Okay, I mean, that's needed. What else? How do I solve it? What else do I need to do? Did you find that table y'all were looking for? What are you going to get from that table?
The KSP.
Okay, what's the KSP of it?
4 times 10 to the minus 54.
Ooh, that's tiny, yeah. 4.0 times 10 to the minus 54. Okay, now what? That's all the easy stuff.
Would be equal to x squared.
Yes, it's an x squared. How do you know?
Because KSP is equal to the concentration of Hg times the concentration of sulfur.
You can tell from that solubility table
So then it'll be
that it's mercury 2 sulfide. When it dissolves, it's mercury 2 ions and sulfide ions. And so when we did that ice table, it would be X mercury and X sulfide. So the KSP would be equal to X squared. Is that all ringing a bell? Okay. So we know that KSP is equal to the concentration of the mercury times the concentration of the sulfide. We know that that's going to be X squared. We know the KSP is 4 times 10 to the minus 54. So if we solve for X, X gives us a number that is called the molar solubility. And X is, good. What number do y'all get?
2 times 10 to the negative 27.
Yep, 2 times 10 to the minus 27. And that's the molar solubility. And when we started working this one and solubility, Salomon, you said solubility is grams per liter. So what do I do with that number? Molarity is really, that is really moles per liter. Yes, what do I need to do with that to get it to grams per liter? Moles to grams, right? Don't I need to multiply it by the molar mass, which y'all said is 232.656. And so the solubility is, we'll go 4.7 times 10 to the minus 25 grams per liter. Is that what you got? Okay, that's it. That is what we were doing, guess it's been a week ago now. It's been a week.
I can't find my solubility table.
It's the other one, yeah. I don't know if I have.
I have the KB to H at the top. That's the basis.
And I'm using the one in the book. I don't even,
I don't have it either.
it would have been the first one I gave y'all with the KA and the KB.
I guess I left it at home.
Okay. Okay, what do you think would happen? Like this is the solubility of mercury 2 sulfide. That means if I have a liter of water, I could get 4.7 times 10 to the minus 25 grams to dissolve. I mean, we could not even measure that, right? It's very insoluble. But that's the solubility. When I say calculate the solubility of mercury 2 sulfide, that's when we're putting it in water. Everything we've done so far is calculating the solubility of it in water. If I scroll back to what we did last time, we calculated the molar solubility of barium fluoride. All that was in water. We calculated the molar solubility of copper 1 bromide. That was in water. So what if I needed to calculate the molar solubility of, I was going to do lead 2 sulfate in sulfuric acid. Lead 2 sulfate, what's the formula for it? PbSO4. So you guys could write an equilibrium reaction, I think, for how that dissolves in water. Yes? What will that look like? PbSO4.
PB plus 2 SO4 minus 2.
Pb plus 2 aqueous, SO4 minus 2 aqueous. Okay? So what we were doing last week is we were doing these ice tables where, do y'all remember I said we start with some lead 2 sulfate, X amount ionizes, and we make X lead and X sulfur, and that's how we ended up with what y'all just told me on the previous one, that this is also an X squared one. But what we assumed when we're doing it in water, and we assumed correctly, we assumed that we're not starting out with any lead or any sulfate. Because when it's in water, there are no other ions there. But y'all, this one's not in water. This one's in sulfuric acid. So there is what is called a common ion. What's the common ion? The sulfate. So, and I just realized as I'm talking through this, when I tell you it's in sulfuric acid, I need to give you a concentration. What if I told you it's in, y'all add this to it, 0.15 molar sulfuric acid? So what that means is that the sulfate is the common ion. So I'm no longer starting with 0 sulfate. Now I'm starting with 0.15 molar sulfate. That means at equilibrium, I'll have X amount of lead, and the sulfate is gonna be 0.15 plus X. Do y'all think, if I'm trying to dissolve lead 2 sulfate in water versus this one where I'm trying to dissolve lead 2 sulfate in sulfuric acid, in which case do you think more lead 2 sulfate would dissolve? In water or in sulfuric acid?
Water.
It's water. It's really a Le Chatelier's principle thing. Because if you start out initially with no sulfate, do you guys see that the equilibrium is going to be pushed to the product side? But in this case, if I start out with some sulfate there, does it make sense to you guys that the equilibrium is going to shift back to the reactant side? Not as much would dissolve. So what the KSP is going to look like then, y'all know that the KSP would be equal to the concentration of the lead times the concentration of the sulfate. And if we take our information from this ice table, it means the KSP is equal to lead, which is X, times the sulfate, which is 0.15 plus X. And anytime we have an ice table that had a little plus X on the equilibrium line or a minus X, what did we always do when we were doing like the pHs of weak acids and weak bases? What did we always do with that little plus X or minus X? We took it away because we are going to make an assumption that X is going to be so small that, like in this one, when I try to add it to 0.15, it's going to be so small it's not going to make a difference. Okay, so we're going to take it away, and it says calculate the molar solubility. We're going to solve for X. What's the KSP of lead 2 sulfate?
1.8 times 10 to the -8.
Yes. So we got 1.8 times 10 to the minus 8 is equal to X times 0.15. X is 1.2 times 10 to the minus 7 molar. Agree with that calculation? That number? Okay. To prove what you guys said earlier, can you also calculate the molar solubility of the lead 2 sulfate in water? Tell me when you get an answer. Just tell me your answer.
1.3 times 10 to the negative 4.
Yes, 1.3 times 10 to the minus 4. Did y'all get there quick?
Yeah, I was just trying to check myself.
Okay. So if it's in water, do you guys agree that the KSP is equal to X squared? Because it's the lead times the sulfate. So it's just X squared. And so we would say 1.8 times 10 to the minus 8 is equal to X squared. And X is the molar solubility, which is 1.3 times 10 to the minus 4 molar. It's what you guys said. When I said in red, if I put it in sulfuric acid versus in blue, when I put it in water, where is it more soluble? Well, clearly the answer in blue is 1,000 times bigger than the answer in red. Okay, so when you have a common ion, you decrease the solubility. And that's how you work with a common ion. Now, let's look at predicting a precipitation reaction. Tell me what a precipitation reaction is. What does that mean?
A reaction in which you see that two aqueous solutions and then get precipitate.
Yes. Yes, a reaction in which you combine two aqueous solutions and they produce a precipitate. A precipitate, y'all will recall, is a solid formed in a chemical reaction. So you have to, this KSP table, you have to meet the KSP in order to have a precipitate. Do y'all remember when we first introduced equilibrium? Do y'all remember calculating a reaction quotient, a Q? Reaction quotient was calculated exactly like the equilibrium constant. You remember that? And what we would do is we would calculate the Q and we would compare it to the KSP. And if the Q was bigger than the KSP, it meant that the reaction was moving in reverse. But if the Q was smaller than the KSP, it meant the reaction was moving forward. Recall all that? That was chapter 15. So, to predict a precipitation reaction, we're going to have to calculate a Q. And here's going to be the setup of that. Will precipitation occur? I'm just going to do PPT for precipitation. Will precipitation occur when, I don't know, 55.0 milliliters of 0.100 molar I don't know why I'm having so much trouble. Sodium chloride is added to 325 milliliters of 0.200 molar silver nitrate. All right, and I'm setting this one up. I'm going to make y'all think through a little bit more than normal. If I mix sodium chloride with silver nitrate, can y'all tell me what the products are without writing it down? You don't have to do it without writing it down. I just want to see if you can. Can you tell me what the products are when I combine sodium chloride and silver nitrate?
Sodium nitrate and silver chloride.
Yes, the products are sodium nitrate and silver chloride. Okay? Now, back in Chem 1, y'all would have a solubility table. And you would look up. Okay, y'all, sodium chloride's aqueous. Silver nitrate's aqueous. But you would have to look up the sodium nitrate and silver chloride to see which one's aqueous and which one's a solid. You don't have a solubility table, but you have a KSP table. So look at your KSP table. Is sodium nitrate on there
No.
or silver? Let me see if I can find you.
Chloride.
Hang on, let me see if I can find James.
I assume I was just using it.
I did. That's it? You were using it to work out?
Because I keep all my stuff in this folder, but.
Okay, so y'all are looking for silver chloride and sodium nitrate. Only one of them's on there, and it is
Silver chloride.
silver chloride. Okay, so when we say, will precipitation occur, we know we're looking for, will silver chloride precipitate? What is the KSP? Is it on there, James?
Silver chloride?
Is it on y'all's sheet?
Yeah.
Okay.
8.1. That's silver carbonate. Yeah.
KSP, yeah. Are we all looking at 1.6 times 10 to the minus 10? Okay, I just want to be sure we're all on the same number. Okay, do you guys agree that that KSP is calculated by taking the concentration of the silver times the concentration of the chloride? Okay, now, we don't want to know the concentration of the silver we start with. Because, see, the concentration of the silver we start with, y'all, is 0.2 molar. That's not what we need. We need to know what the concentration of the silver is when all this stuff is combined together. Okay? So, to figure out the concentration of the silver, you are going to use a handy little formula that you learned in Chem 1. You're going to do M1V1 is equal to M2V2. Where's the silver coming from? The silver nitrate. So do you see that M1 is going to be 0.200 molar? What do you think V1 is going to be? 325 milliliters. What's M2? We don't know. That's what we're solving for. What's V2? It's what, Alexandria? Yes, it's the total volume, the 325 plus the 55. So V2 is 347 milliliters. Okay, now notice, when I did M1V1 is equal to M2V2, nope, can't add, can't add. Thank you for looking at me funny, Alexandria.
I was wondering, I was
Let's say
like,
340.
What is it?
adding
Thank
It's
you.
not complex enough.
No, it's just, no, I totally punched in. I added 22 instead of 55. Now, if y'all can explain to me why my brain did that, I don't know. But anyway, what was I saying? Oh, M1V1 equals M2V2. Y'all look, you can leave it in milliliters. If both of your volumes are in milliliters, do y'all see those are going to cancel out and you're going to be left with molarity? Okay, so, have y'all already done that math? M2 is 0.171 molar. That's the concentration of the silver. Can you guys calculate the concentration of the chloride?
A lot less. Right?
Yeah, because we're only using 55 milliliters of it, right? .0145 molar.
Yeah.
Yeah. All right, we got to calculate a reaction quotient. How do you calculate the reaction quotient? Alexandra's got me concerned because she's looking at me with a really, she does not like my numbers. Are others on the right side of the screen? Is all that right?
Yeah, that's what I put.
Salomon and James said yes. Huh? Okay, how do you calculate a reaction quotient?
Products over reactant.
Yeah, it's still products over reactant, raise the power of the coefficient. It's also calculated exactly like the KSP.
It says solid.
So calculate the Q using those numbers that we just calculated. The concentration of the silver is 0.171. The concentration of the chloride is 0.0145. Yeah, I'm gonna do it in scientific notation. It does not matter, I'm just gonna do it that way. Yeah, 0.0025 or 2.5 times 10 to the minus 3. Remember, a Q, just like an equilibrium constant, y'all, it's unitless. Okay, so we get 2.5 times 10 to the minus 3. Compare the Q to the equilibrium constant. Compare the Q, which is 2.5 times 10 to the minus 3, to the equilibrium constant, which is 1.6 times 10 to the minus 10. Clearly, which one's bigger? Q. If Q is larger than the KSP, then which direction is the reaction going? It's going in reverse. What reaction are we talking about? Y'all, this is the reaction that we're talking about, isn't it?
Because you would need more, I guess, reactants in that equation to make it go back towards the reactant side, because they're in the.
Yes, because they're in the denominator, right? So if Q is bigger than the KSP, I heard y'all say it, you all agree that it's going in reverse, correct? What does reverse do? Reverse forms a precipitate. So what was the whole question we were asked? Will a precipitate form? Yes. If Q is larger than the KSP, then the answer is yes, a precipitate will form. If Q is less than the KSP, then which direction is it going? It's going forward. And that forward means everything's aqueous. It means no precipitate will form. Okay, plain and simple? Do y'all feel it simple? Okay. Now, factors that affect solubility. One factor that affects solubility, we've actually calculated it already today. It's the common ion. If you're trying to dissolve something in a solution that has a common ion, what happens to the solubility? Solubility decreases in a solution that has a common ion. We actually calculated that with the lead 2 sulfate in the sulfuric acid. If there's a common ion present, solubility decreases. A second factor that can affect solubility is the pH. How does the pH affect the solubility? Well, it depends. So dig back to, we're on chapter 17. Dig back to chapter 16. How do y'all know if a salt is a neutral salt?
Weak acid,
It's a
strong
strong base and strong acid.
A strong base and a strong acid makes a neutral salt. Okay? If the salt is neutral, then adjusting the pH of the solution will do nothing to its solubility. Okay? So for neutral salts, the pH has no effect on solubility. No effect. Affect? Yeah.
No,
I
wouldn't
could
it be
try
affect?
to figure
I
out
use
those
the
long
change.
term.
Oh, y'all, I'm with you.
Like
I don't
affect
know.
is like affecting someone you're affecting directly. Affect is like cause and effect. It is a cause of like, or it is an outcome.
Okay.
Effect.
Did I use the right
Like
form?
affect is like, I'm affecting you by
I
shoving.
feel like I have it figured out when I read something. and it'll be
I,
like,
I'm the same way. I feel like I get it and then it,
I've heard the explanation a million times,
Uh-huh.
I still never get it.
Yeah.
and it's not so straightforward as verb and
You
noun.
can just write influence.
Yeah, just change the word entirely. We don't use it.
I'm so gonna do that from here forever. It has no influence on the solubility.
I can explain the difference, but at the same time, like there wouldn't be a point because it still sounds the same.
It sounds the same, but in writing, I want to,
You want to be more accurate.
yeah, I want to write it correctly. I mean, I have all my students reading it, and I don't want them to think she doesn't know what she's talking about because she doesn't know the difference between affect and effect.
I just write whatever I feel like at the time, to be honest. Like,
Yeah, but I'm standing up here in front of all y'all right now. I want to be, I don't want to write.
it's just influence.
That's what I'm gonna do. That's what I'm gonna do. Okay, so how does pH affect solubility? Neutral salts, no influence. Y'all, if the salt is basic, here's how you make it more soluble, okay? This is how I think of it. If the salt is basic, you've got to go the opposite direction to make it more soluble. So if the salt is basic, you've got to make it more acidic and more will dissolve. Okay? If the salt is basic and you make the pH go up, then it's going to be less soluble. Do you see? But how I do it is I always remember a basic salt, lowering the pH makes the salt more soluble. And if you just know that, then you know that then raising the pH makes the salt less soluble. And how I keep it straight is I just go here. You got to know what your salt is. You go opposite that to make more dissolve. You following? So, if the salt is acidic, how would you make more dissolve? Increasing the pH. Make the pH go higher. Make it more basic. Increasing the pH makes the salt more soluble.
Basically, it just has to go the opposite direction.
Yes, it has to go the opposite direction of what the salt is. And it honestly, it all goes back to Le Chatelier's principle. If you carry it the opposite direction, it makes more dissolve. Okay? The other factor that affects pH, and I'm actually not going to lecture on it at all, it's the formation of a complex ion. That is what you guys are doing today in lab. You're going to be working with, what did we say, copper, manganese, iron, and cobalt. And you're going to be forming complex ions that are going to precipitate. You're going to have the instructions for how they precipitate. And the formation of those complex ions, it's precipitates that confirms the presence of those ions. Okay? And it's complex ions, so it's some complex chemistry. That was a joke. Okay? The who?
We would have gotten it any other day.
Okay, okay. I did tell y'all end of chapter 16 problems, because that's when I got some that were like wrong in the book and all that stuff. Okay, yes, so we skipped them. This is the end of chapter 17, right here. End of chapter 17. These start on page 900. They are numbers 5, 9, 11, 13, 15, 17, 27, 29, 35, 49, 51, 55, 57, 65, 67, and that is all. That's all. Okay, hang on.